Struggling with physics? You have come to the right channel. This is Physics is Easy with Mr. Jesse. This tutorial is on Chapter 27, Section 5, The Dual Nature of Light and Matter. For this lesson, we are going to discuss de Broglie's theory about the dual nature of light and matter, calculate the momentum of a photon, calculate de Broglie's wavelength, and calculate the frequency of waves produced by matter. To formally begin this lesson, I would like to show you one of my most favorite videos in physics that shows the dual nature of matter. This video has a very strong impact in my life because it basically changed the way I view the world. Here it is.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this. Two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, The electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
It was a French scientist named Louis de Broglie who was able to discover the wave nature of electrons, and because of this, he was awarded the Nobel Prize in Physics in 1929. So based on the previous video, electrons can either behave as a particle and it could also behave as a wave. And now I'm going to introduce you the equations that we are going to use for this lesson. The first is the momentum of a photon. Now, how does a photon have a momentum? So, according to what we have discussed, if this is a photon and we have here a metal surface, as the photon hits the metal surface with enough energy, it is possible of liberating or freeing the electrons in the metal surface. So if this is the electron here, and not only that, the photon can possibly give this electron kinetic energy, allowing it to move. So it's just if they were billiard balls hitting each other, and in the context of billiard balls moving and colliding, there is actually momentum. Without deriving for the equation, the momentum of a photon is equal to E over C, where P is the momentum of the photon, E is the energy of the photon, and C is the speed of light. Now, we could further expand this equation in terms of this. So, E is actually HF, and F may be expressed in terms of C over lambda. So, eventually, we could say that the momentum of a photon is equal to HF. And where h is the Planck's constant, f is frequency of the photon, and lambda is equal to the wavelength, p is equal to h over lambda, where lambda is the wavelength of the photon. Moving on, de Broglie suggested that all material particles with momentum p should have a characteristic wavelength, and therefore the de Broglie wavelength of a particle is lambda is equal to h over p, and that is equal to h over mv, where p, or the momentum, is actually equal to the mass of the object multiplied by its velocity. Further, de Broglie postulated or suggested that the frequencies of matter waves, that is, waves associated with particles having non-zero rest energy, so particles having non-zero rest energy are actually photons. So when we talk about matter waves, for example, when electrons behave as a wave, then we call them matter waves. He said that matter waves would also obey Einstein's relationship of the photons, which is E is equal to hf, and therefore the frequency of a matter wave can be written as F is equal to E over h, where F is frequency of matter wave, E is the energy of the matter wave in joules, and h is the Planck's constant. Here is a sample problem. Compare the de Broglie wavelength for an electron with mass equal to 9.11 times 10 to the power of negative 31 kilograms, moving at a speed equal to 1.0 times 10 to the power of 7 meters per second with that of a baseball, of mass 0.145 kilograms, pitched at 45 meters per second. So we have the equation for the de Broglie wavelength, that is equal to lambda is equal to h divided by the product of mass of the object multiplied by its velocity, or simply the momentum of the object. So solving for the wavelength of the electron, we just have to substitute our values. We have the Planck's constant, that is equal to 6.63 times 10 to the power of negative 34 joules second divided by the mass of the electron. So we will have the mass of the electron, which is equal to 9.11 times 10 to the power of negative 31 multiplied by the velocity of the electron in meters per second. So that's 1 times 10 to the power of positive 7. This gives us a value of 7.28 times 10 to the power of negative 11 meters. This means then that in order for us to solve for the wavelength of the baseball, we'll call that lambda b, that would be equal to the Planck's constant divided by the mass of the baseball multiplied by the velocity of the baseball. So substituting those values, we will have 6.63 times 10 to the power of negative 4 for our Planck's constant, divided by the mass of the baseball in kilograms, that's 0.145 kilograms, and its speed, which is 45 meters per second. That gives us 1.02 times 10 to the power of negative 34 meters. So what do these values imply? Now if you notice, the wavelength, the de Broglie wavelength of the electron is way bigger compared to the de Broglie wavelength of the baseball. In fact, if we are going to look at this number here, 1.102 times 10 to the power of negative 34, it is relatively a very small number, almost negligible. So this means that it is very unlikely for us to observe a baseball behaving like a wave because its wavelength is nearly zero. However, an electron having a de Broglie wavelength of 7.28 times 10 to the order of negative 11, that means that it is more likely that we could observe the electron to behave as a wave rather than that of the baseball. So this means that the greater the de Broglie wavelength, then the more likely it is that we could observe that particular matter to behave as a wave. To summarize, the de Broglie equations show the dual nature of matter, that matter can either be a particle or a wave. Now, it is a particle because it contains matter concepts like energy and momentum. However, it is also possible for matter to contain wave concepts like wavelength and frequency. At this point, kindly go to WebAssign and answer the task entitled Dual Nature of Matter. Once again, always remember, physics is easy with Mr. Jesse.